The impact of carbon dioxide in the atmosphere. A simplistic primer. A very smart engineer friend asked me some good questions about carbon dioxide in the atmosphere. I thought I knew the standard answers, but was not certain. So I found some basic data on the internet and did some basic calculations. I'm not a climate scientist or a scientist at all, but the results might be useful to you, and you can do these calculations yourself if you wish. This does not prove that climate scientists are correct. It does provide a starting point for seeing which issues are most complicated. This lecture script is available as a PDF. The link is in the description of the video. Attributions for the images are given in the lecture script PDF. Questions. Why does absorption by carbon dioxide in the atmosphere heat the Earth, not cool it? How plausible are the following? 100% of atmospheric absorption at carbon dioxide wavelengths. Absorption and reradiation of 1 watt per square meter of power. Raising Earth's temperature by 1 degree Celsius. Reducing emissions is very difficult, costly, and political. A good question is, how much heating can be averted by reducing emissions? We won't be able to quantify this last question, but we will come to see why it is a difficult issue. I did calculations that say that carbon dioxide's 15 micron wavelength contributes strongly to greenhouse effect heating. The 2 and 2.7 micron wavelengths contribute to cooling, but are weak. The 4.3 micron wavelength absorbs strongly, but contributes nearly equally to heating and cooling. We will see that. The total effect of carbon dioxide summed over all wavelengths calculated to net heating when the average temperature of the Earth's surface was above -70 Celsius, consistent with climate scientists' explanations. However, we will see how the impact of continuing to add carbon dioxide to the atmosphere is too complicated for simplistic analysis and is central to skepticism or denial of man-made climate change. Gases in the atmosphere that absorb and re-radiate infrared photons would do so for radiation from the sun as well as thermal radiation from the Earth. Why should this cause heating and not cooling? A good question. I thought that it would be relatively straightforward to show that carbon dioxide has much greater greenhouse effect heating the Earth than cooling it by re-radiating infrared from the sun. I did simplified calculations which confirmed greenhouse heating, as climate scientists say, but it's complicated, and my assumptions were necessarily simplistic. I am trusting data, charts, and information from Google search without checking for authoritativeness. Molecules, dust, aerosols, and clouds in the atmosphere absorb electromagnetic radiation at specific wavelengths, ranges, or bands, as we will see, whether the radiation comes from the sun, the surface of the Earth, or from the atmosphere. When a molecule in the atmosphere absorbs a photon of some specific wavelength, some sources say that the excited molecule then re-emits a photon at the original wavelength in a random direction, re-radiates isotropically. This is wrong or too dumbed down. Other sources say the molecule collides with other molecules, the energy thermalizes at the local temperature, and eventually a thermal photon is emitted in a random direction. Once the original wavelength is absorbed, the atmosphere returns some energy toward the original source, which would not occur if there were no absorption and the atmosphere were completely transparent. If the original absorbed photon was from the sun, the effect of the absorption and reradiation is to reduce the amount of radiation reaching the surface of the Earth, a reduction of heating, so a cooling effect. If the original absorbed photon was from the surface of the Earth, the effect of the absorption and reradiation is to reduce the amount of radiation reaching the top of the atmosphere and escaping to outer space, an increased heating of the atmosphere and Earth's surface, called the greenhouse effect. This diagram shows several cases. For wavelengths for which the atmosphere is transparent, the photon will pass through the atmosphere, either from the sun to the Earth's surface, or from the Earth's surface to outer space, or if the photon was emitted from a molecule in the atmosphere, it will either escape to the Earth's surface or to outer space. The brown example is wavelengths for which the atmosphere is opaque. Photons emitted by the sun will be absorbed in the atmosphere. Photons emitted from the surface of the Earth will be absorbed in the atmosphere. Photons emitted by molecules in the atmosphere will generally be absorbed in the atmosphere unless they are close to the surface of the Earth or close to the top of the atmosphere. Neglecting clouds. For the infrared range corresponding to thermal emission from the Earth's surface or from molecules in the atmosphere, there are wavelength ranges with 100% absorption or scattering by the atmosphere, opaque, and other wavelength ranges that are fairly transparent. For our purposes, the gross effect across the Earth's thermal emission range is that about half the incident radiation passes through the atmosphere and about half gets returned toward the source. Better numbers won't change our basic calculations. Clouds reflect some sunlight back to space, part of Earth's albedo. If there were albedo but no greenhouse effect, Earth would be something like 66 degrees Fahrenheit or 37 degrees Celsius cooler than it is. Venus would be 900 degrees Fahrenheit or 480 degrees Celsius cooler if it had no atmosphere. Most of the greenhouse effect on Earth is due to water vapor and clouds, and long ago raised the temperature on Earth beneficially to life. But the relatively small effect from carbon dioxide and methane that has accumulated in the last 100 years is said to have produced an energy imbalance of about 1 extra watt per square meter from the atmosphere to the surface of the Earth that is said to be the cause of recent warming of the Earth, melting glaciers, thawing Arctic permafrost, and thinning Arctic ice pack. We have not reached steady state for the current conditions, but that's going beyond today's exercise. Carbon dioxide absorption bands. Let's start with this diagram. The red curve here is the thermal spectrum emitted by the sun. The orange area is sunlight that reaches Earth's surface after greenhouse gas molecules, dust, aerosols, and clouds in the atmosphere scatter or absorb some of the sunlight. The orange area is beneath the red curve. Reduction of sunlight reaching the Earth has cooled the Earth, but this is only part of the whole picture. For these diagrams, this is the visible range of light, and this is the infrared range of light. The greenhouse effect takes place for the infrared range. The magenta, blue, and green curves are thermal spectra for thermal emission from Earth's surface at different temperatures. The blue area is thermal emission from the Earth's surface that reaches outer space and escapes after the atmosphere scatters or absorbs some of the infrared radiation. The blue area is beneath the blue curve. Reduction of thermal emission from Earth's surface reaching outer space has heated the Earth. Notice that for this wavelength range, 10 to 12 microns, a lot of infrared radiation from the surface of the Earth makes it to outer space. Which is to say that the atmosphere is transparent. But in this range, and this range, and this range, very little infrared radiation from the surface of the Earth makes it to outer space. There the atmosphere is opaque. The gray area is the absorption and scattering by the atmosphere between Earth's surface and outer space in either direction. Many wavelengths have 100% absorption or scattering between the top and bottom of the atmosphere. This range here, from say 14 microns to 70 microns, is totally absorbing. So is this range and this range. But this window is relatively transparent. The cyan area is absorption and scattering by water vapor, the strongest greenhouse gas with the most impact on Earth's temperature. So, fully absorbing, fully absorbing, fully absorbing. Notice the water vapor window from 7.5 microns to 20 microns, and that the peak of thermal emission from the surface of the Earth is within this water vapor window. The brown or mustard area is the absorption by carbon dioxide. Here, 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 and here. This diagram also shows absorption by ozone and methane, but we're not going to consider those in this video. Let's switch to this diagram, which puts water vapor and carbon dioxide on the same graph. Blue-gray for water vapor, brown for carbon dioxide. Notice the water vapor window here, and that carbon dioxide has an absorption band within the water vapor window. We will assess the 4 carbon dioxide absorption bands centered around 2 microns, 2.7 microns, 4.3 microns, and 15 microns. Note that the 2.7 micron band coincides with 100% absorption by water vapor, but the other bands do not. The 15 micron band is within the water vapor window, where thermal emission from the Earth is high. Since there is radiation from the Sun and from Earth's surface, atmospheric absorption and isotropic reradiation at a given wavelength has both a warming and cooling effect, but not equally. I calculated that wavelengths shorter than about 4.2 microns, here and to the left, are net cooling for Earth, and wavelengths longer than that, so here to the right, are net heating. But this assumed a constant temperature for Earth's surface and atmosphere. Further from the crossover is greater imbalance. I will identify which absorption bands I think are net cooling versus net heating. Later I will try to quantify the amount of power returned to the Earth. Absorption cross-sections. Different wavelengths for a given molecule have different absorption, differing by 100 or 1,000 where there is absorption. This is a graph of carbon dioxide's infrared absorption cross-section in centimeters squared per molecule versus wavelength in microns. A larger value means higher probability for absorption. Absorption is due to quantum mechanical, quantized, rotational vibrational states and is messy. Each unique vibrational state is accompanied by a forest of rotational states. I'll call each spiky forest a band for ease of wording. This is not the same as an electronic band in semiconductors. These graphs are a composite of 10 partial pressures and 3 temperatures. The absorption at a point in the atmosphere is a function of wavelength, composition, concentration, pressure, and temperature, and cloud for water vapor and aerosols for some molecules, but not for carbon dioxide. Climate modeling must use data at different pressures and temperatures. There are 7 graphs. Here we're seeing the first 3. The 7 graphs have different scales. In case you cannot read the scales are 10 to the minus 18, 21, 21, 18, 21, 21, and 18. The first graph shows 2 microns to 18 micron wavelengths on one graph. The 4.3 micron band looks strongest, then the 15 micron band, though it also has a wide band of lower cross-section. The 2.7 micron band is weak, and we cannot see the 2 micron band on this graph at all. The other graphs show detail for each band. This graph is the 2 micron band graph with scale 10 to the minus 21. Then the 2.7 micron band graph. Then the 4.3 micron band with scale 10 to the minus 18. We will skip the next 2 graphs, which are low absorption wings of the 4.3 micron band. The final graph is the 15 micron band with scale 10 to the minus 18. I will approximate those graphs as the following absorption bands. The number after the colon is my crude estimate of the area under the absorption curve for that band. The width of the band times the average absorption cross-section for the band, in units of micron centimeter squared per molecule, divided by the value for 4.3 microns. So these values are proxy estimates for the relative amount of absorption if the same radiation spectral density were present at each band, which will not be the case. The 4.3 micron band seems a little stronger than the 15 micron band, but there's 50% uncertainty in my estimates there. And the other two bands are much weaker, a factor of 100 weaker and 10,000 weaker. Spectral density. Now we calculate the blackbody radiation spectral energy density per unit wavelength, present for each carbon dioxide wavelength for sunlight at the top of the atmosphere and thermal radiation from the Earth into the lower atmosphere. I used the sun photosphere temperature of 5,772 Kelvin, which would have a spectrum peak of 1/2 micron wavelength visible, which is smaller than these four carbon dioxide absorption bands. However, some graphs use other temperatures such as 5,250, 5,500, 5,525, trying to match the data. This difference doesn't much matter. I used a mean surface temperature of plus 15 Celsius for the Earth, which would have a spectrum peak at 10 micron wavelength in the infrared. So here, between the 4.3 micron and 15 micron carbon dioxide bands. Of course, the temperature of the Earth's surface is not uniform or constant, nor is temperature within the atmosphere, so this is too simplistic. Using an average temperature may not be good enough. I used Planck's blackbody spectral energy density formula. The results are in joules per meter to the fourth. In this formula, lambda is the wavelength of the radiation, and T is the temperature of the radiation, so either from the sun or from the Earth. Alternatively, I could have used the formula for spectral radiance. This would have a constant multiplicative factor and units of watts per cubic meter steradian, but no change to the argument. At each carbon dioxide absorption wavelength lambda, and for the temperature T of the sun or the Earth, I calculated the spectral energy density. I divided the solar values by the square of the Earth's distance from the sun divided by the sun's radius to get the solar value at the top of Earth's atmosphere, at a point directly in line between Earth and sun, where the sun is directly overhead. Then I divided that solar value by 4 to get the average value across the sphere of the Earth, day and night sides. The the area of the sphere is 4 pi r squared. The area of the cross-section of the Earth is pi r squared. Here are my calculations. The first value after the colon is for sunlight at the top of the atmosphere, averaged across the Earth, including the night sun, the night side. These values decrease with longer wavelength, further from the sun's peak wavelength of 1/2 micron. So 3 by 10 to the minus 1, 1 by 10 to the minus 1, 2.4 by 10 to the minus 2, 2 by 10 to the minus 4. The second value after the colon is for thermal radiation from the Earth's surface into the lower atmosphere, with a peak wavelength at 10 microns. The 4.3 micron value, 2.8 by 10 to the minus 2, is about 10 times smaller than the 15 micron value, 2.4 by 10 to the minus 1. The 2.7 and 2 micron values are much smaller. The third value after the colon is the Earth value minus the Sun value. Positive for net heating, negative for net cooling. The crossover for this calculation is about 4.2 microns at plus 15 degrees Celsius. The 2 and 2.7 micron lines would absorb and re-radiate much more infrared radiation incoming from the sun than outgoing from the Earth's surface, so contribute to cooling the Earth. However, the 2.7 micron line is already opaque from water vapor, so carbon dioxide has minimal impact there. The 15 micron line would absorb and re-radiate 1,000 times more infrared outgoing from the Earth's surface than incoming from the sun, so contribute to heating the Earth, the greenhouse effect. The 4.3 micron line has mixed effect, absorbing and re-radiating only slightly more from the total Earth at constant plus 15 Celsius than from sunlight hitting the daylight side, so my analysis is too simplistic, particularly using an average temperature for Earth's surface. The crossover temperature for the 4.3 micron line calculated to 11 Celsius, so higher latitudes or colder layers of the atmosphere contribute to cooling. Now we multiply the third number from this table, Earth minus Sun, with the number from the earlier cross-section table. For 2 microns, we get minus 4 by 10 to the minus 5, which is a small cooling effect. For 2.7 microns, we get minus 1 by 10 to the minus 3, a larger cooling effect. For 4.3 microns, we get plus 4 by 10 to the minus 3, a small heating effect, but we assumed constant temperature over the Earth, so that analysis is overly simplistic. For 15 microns, we get approximately 1.6 by 10 to the minus 1, which is a significant heating effect, though there's also a 50% uncertainty. The 15 micron wavelength band causes 100 times more greenhouse heating than the cooling effect from the other bands. This is because it is close, a factor of 1.5, to the 10 micron peak for Earth's thermal radiation, and has a high absorption cross-section. The 4.3 micron band has a high absorption cross-section, but it is near the crossover wavelength between sunlight and the Earth's thermal radiation, so it cools and heats comparably, averaged over the Earth. My calculation was that the 4.3 micron band net heats at 15 Celsius, but net cools below 11 Celsius, such as at higher latitudes or colder layers of the atmosphere. A better analysis should take into account temperatures across the Earth and the atmosphere temperature profile. The total effect of carbon dioxide summed over all wavelengths calculated to net heating when the average temperature of the Earth was above minus 70 Celsius, consistent with climate scientists' explanations. Planet Venus has a carbon dioxide atmosphere and is much hotter than the Earth, and not because it is closer to the Sun. All 4 carbon dioxide absorption bands are net heating and more strongly than on Earth. On Venus, the crossover wavelength calculates to 1.5 microns at present temperature. Venus had runaway greenhouse effect billions of years ago that heated it to its current temperature, hotter than the maximum temperature on Mercury, which has only a trace atmosphere. Methane has an absorption line at 7.6 microns, which is greenhouse warming. Climate scientists say that methane is a stronger greenhouse gas than carbon dioxide, but that carbon dioxide remains in the atmosphere much longer than methane, hundreds of years to 1,000 years. So both are important. Water vapor absorption is at or near 100% absorption at methane's absorption band, so the impact of continuing to add more methane to the atmosphere is too complicated for simplistic analysis and has to defer to better modeling. Sulfur dioxide has an absorption line near 7.5 microns, but is not listed as a greenhouse gas. Perhaps this is because it forms sulfuric acid within 2 weeks and then progresses to sulfate aerosols that scatter and absorb in the visible spectrum and cool the Earth, though I don't know the wavelengths. Here is one false argument. The Sun's temperature is higher than the Earth's temperature, so the spectral density at any wavelength will be higher for the Sun's temperature than for the Earth's temperature. This is true for the surface of the Sun and surface of the Earth. But for sunlight spectral density at Earth's orbit, we have to reduce the Sun's spectral density by the square of the appropriate distance ratio. Here is a second false argument. The solar irradiance at Earth's distance from the Sun is higher than the radiation watts per meter squared radiated from the Earth. So maybe the reradiation of radiation from the Sun should always be higher than reradiation of radiation from the Earth. No. Radiation from the Sun intercepts the Earth's disk area, pi r squared. Radiation from the Earth emits from the sphere's surface area, 4 pi r squared, day and night, pole to pole. Taking the factor of 4 into account, Earth's surface radiates something like 15% more power into the lower atmosphere than the Sun supplies to the top of Earth's atmosphere. More than half of the excess gets returned to the surface. Less than half gets radiated to space. Water vapor in clouds give a stronger greenhouse effect than carbon dioxide, but it has bands throughout the visible and infrared spectrum. Clouds reflect sunlight back to space and account for much of Earth's albedo, cooling the Earth. Reflect is the wrong word, but it gives the right idea. Water vapor in clouds re-radiates strongly light from the sun and infrared from the Earth, both cooling and heating the Earth. I guess water vapor in clouds are responsible for much of Earth's albedo, but also most of the greenhouse effect for Earth's history. I assume the amount of water vapor in the atmosphere has been pretty constant over recent millennia, while the amount of carbon dioxide in the atmosphere has increased by 30% over the last 200 years, having previously been fairly constant. However, global warming probably puts more water vapor into the atmosphere. I can't calculate whether the net effect would be cooling or heating, but climate scientists would have modeled it. Increased water vapor in the water vapor window of 7.5 to 20 microns would heat the Earth. The window from 3 to 5 microns might have mixed effect. The windows at shorter infrared wavelengths would have cooling effect. I don't know how clouds and their effects would change. As global warming melts polar ice and Arctic snow, Earth's albedo decreases, reduced reflection of sunlight to space, which heats the Earth. But water vapor in the atmosphere increases, both cooling and heating the Earth. Climate modeling must account for positive and negative feedback effects of increased temperature. Very complicated. Absorption percentage. Let's assume a local peak absorption cross-section near 15 micron wavelength of 5 by 10 to the minus 18 centimeters squared per molecule from the cross-section graph. The cross-section value should depend on temperature and pressure, but I don't have that data. We calculate the number density of carbon dioxide molecules in the atmosphere. For simplicity, we assume dry air and limit ourselves to the troposphere, the lower layer. Assuming ideal gas at 15 Celsius, there are 42.3 moles per cubic meter, or 2.6 by 10 to the 25 molecules per cubic meter. We use 400 parts per million as the current concentration of carbon dioxide, and that gives us 1 by 10 to the 22 carbon dioxide molecules per cubic meter at sea level at 15 Celsius. The absorption depth or length or mean free path equals 1 over the product of absorption cross-section and number density. I calculate an absorption depth of 0.2 meters at sea level at 15 Celsius. This felt pretty low when I got this result. Other sources say that absorption depth is 10 to 20 meters, but I think this is over the wide absorption band, and it may be an average for the troposphere, not specifically the sea level value. There's a couple dozen smaller peaks with absorption cross-section peaks between 1/3 and 1 by 10 to the minus 18. So those peaks would have absorption depth of 1 to 3 meters. And there are valleys between the peaks. So the average absorption depth across the wide band could well be 10 to 20 meters. Therefore, it seems plausible to me that even 1 kilometer of lower atmosphere at sea level would be fully absorbing for 15 micron and 4.3 micron wavelengths for the current 400 part per million of carbon dioxide. However, I'm a little confused by the 2 micron wavelength and its weak absorption. Its peak absorption cross-section is 5 by 10 to the minus 21. I calculate the absorption length as 200 meters at sea level. It would be longer with increasing altitude. I would think this would be 100% absorbing over 10 kilometers, even with altitude dependence, but graphs show it as about 50% absorbing from Earth's surface to space. If the average cross-section for the 2 micron band were 3 by 10 to the minus 22, the absorption depth at sea level would be about 3.3 kilometers. So using more detailed formulas for altitude dependence of density, pressure, and temperature presumably would show that the 2 micron band is not fully absorbing across the atmosphere, but I didn't attempt to show that. 100% absorption. Why would adding more be bad? The most difficult issue is that large portions of the 4.3 micron and 15 micron absorption bands and all of the 2.7 micron band have nearly 100% absorption between the surface of the Earth and the top of the atmosphere. But the 2 micron band and the methane bands are not 100% absorbing presently. Adding more carbon dioxide to the atmosphere supposedly increases heating due to 3 mechanisms, though these seem weak mechanisms to me. Adding more carbon dioxide increases the absorption of wavelengths that are presently not 100% absorbed, such as the wings of the band. So out here and out here. But wouldn't this be a weak impact? Adding more carbon dioxide reduces the absorption length depth, presumably at all altitudes and temperatures. For wavelengths for which the atmosphere is 100% absorbing due to carbon dioxide, reducing the absorption length raises the highest altitude from which there is 100% absorption to the top of the atmosphere for carbon dioxide wavelengths. This reduces the probability for thermal photons emitted within the bulk of the atmosphere to reach the top of the atmosphere and escape to outer space. The effect is further heating of the Earth and the atmosphere. But wouldn't this be a weak impact? Reducing the absorption length depth makes more of the reradiation hitting Earth's surface come from the lower troposphere, which is generally warmer than the upper troposphere. Does this increase the radiated power hitting the surface of the Earth? I don't know. To me, this effect seems weak for wavelengths whose absorption length is already less than a few hundred meters. Also, Antarctica's thermal inversion in the lower troposphere complicates this. So, additional carbon dioxide supposedly increases greenhouse warming, even though parts of the bands are already 100% absorbing. So say climate scientists. But wouldn't these have a weak impact? The effect is weaker than if the bands were not 100% absorbing, so a simplistic calculation has to defer to better modeling. And likely this requires the full complexity of climate modeling. But we laymen cannot really assess climate scientists' science and modeling. Doubt over the actual impact of continuing to add carbon dioxide is central to skepticism or denial of man-made climate change. This is hugely important given the extreme difficulty and cost to significantly reduce carbon dioxide and methane emission. Of course, this is a major political issue as well as scientific, technological, and economic. Absorbed and reradiated power. Let's calculate the power absorbed and potentially reradiated from thermal emission from Earth's surface by the 15 micron band. At 15 Celsius, the spectral radiance is 5.8 million watts per cubic meter per steradian solid angle. Let's take the width of the band of 100% absorption as 1 micron, though it may be closer to 2 microns. Then the atmosphere could absorb and re-radiate more than 5.8 watts per square meter per steradian. I don't know the right solid angle to use here, but let's guesstimate 2 pi over 10 steradians toward the Earth's surface, nearly face on. This would give roughly 4 to 36 watts per square meter back toward the Earth. If correct, it seems plausible that carbon dioxide's greenhouse effect is a significant enough component of Earth's energy balance or imbalance. But this does not say the impact of additional carbon dioxide in the atmosphere. Warming. Climate scientists say that Earth is experiencing an energy imbalance of about 1 watt per square meter excess radiation from the greenhouse effect hitting the surface of the Earth, causing temperatures to increase to move toward steady-state balance. As I understand it, Earth's surface temperature is not yet in balance with carbon dioxide already in the atmosphere, and additional emission increases the imbalance, though I don't know by how much. We can use the Stefan-Boltzmann law to see how much Earth's surface temperature would need to increase to send an additional 1 watt per square meter into the atmosphere. Perhaps as much as half of that additional radiation will escape to outer space, so let's double the temperature increase. I calculated an increase of 0.6 degrees Fahrenheit or 0.36 Celsius. This is simplistic as climate is a complicated system with emissivity, albedo, thermal inertia, clouds, absorption, transmission, non-uniform, non-constant surface temperature, atmospheric conditions, varying with altitude, amplifying effects, and negative feedback. Earth's average surface temperature has increased by around 2 degrees Fahrenheit in recent decades, shown here. If atmospheric carbon dioxide doubles in future from 400 part per million to 800 part per million, climate scientists say that Earth's surface temperature will increase by another 5 degrees Fahrenheit or 3 degrees Celsius. That being said, one 2024 non-mainstream paper claimed that if world carbon dioxide emissions could be driven to zero by 2050, this would only avert an increase of 1/3 of a degree Celsius at immense cost, difficulty, and inconvenience to reduce those emissions. But I believe that paper did not take clouds into account. I don't know whether their conclusion is accurate, but I would think climate scientists should work to reach a strong consensus on the actual effect of reducing carbon emissions and then communicate it to us. They have very complex models, but one of their major hurdles is the quantification of the various feedbacks and tipping points. It is the feedbacks and tipping points that account for the bulk of the uncertainty in real-world warming potential. Climate change skepticism and denial. To me, as a non-scientist layman, the only aspect of climate change for which skepticism may be warranted is how much surface heating can be averted by how much reduction in carbon dioxide and methane emission, fully taking into account clouds, melting of glaciers, thinning of Arctic ice pack, thawing of permafrost, Antarctica thermal inversion, change to the Gulf Stream, jet stream, etc. On the other hand, I see no basis to deny that the global average temperature has increased significantly in recent decades, that it correlates with atmospheric carbon dioxide, but correlation is not proof of causation, and that consensus among climate scientists is that the heating is caused by increased carbon dioxide and methane, though the consensus is not unanimous and there are uncertainties. I'm not a climate scientist or a scientist at all, and I could have made foolish mistakes or failed to understand subtle but critical issues. I accept what mainstream climate scientists are telling us, but the significant adverse impact of continuing to add carbon dioxide to the atmosphere is predicted not by basic calculations but by complex climate models that we laymen cannot really assess. We either accept their conclusions or are skeptical or deny them. I hope this video has given you useful information. My other videos are various physics courses.